Nice. Our next speaker will be Simon McClusky, um, uh, Associate Professor. Simon McClusky is a geodesist and a senior fellow at the Australian National University. He uses real-time satellite measurements in terms of precise point positioning and gravity field measurements to measure tectonic plate motion and the spatio-temporal changes in the Earth's crust and mantle. He was awarded 12 major research grants as a co-lead and 2 more as a primary investigator. I will now leave the floor.
Thanks, Leo. Can everybody hear me okay?
Yes, and we see your presentation.
Yeah. Just by way of a correction to my introduction, I am an honorary associate professor at ANU, and I'm an ongoing geodesist at Geoscience Australia currently. So the presentation I'm going to make today is basically looking at Australian perspectives on the use of GNSS for tsunami warning. This presentation is a collaboration between the Positioning Australia branch at Geoscience Australia and the Community Safety branch at Geoscience Australia, who operates the earthquake warning system that Australia runs. And also I'm going to show some work by Professor Xin-Shan Han at the University of Newcastle in Australia. So just by way of an overview, I'm quickly going to show an introduction of the tsunami hazard in our region. I'm going to quickly run through what the Australian government is currently doing for its tsunami warning capability, and then talk about what an ideal capability might look like. I'm going to look at a few future opportunities using ground-based GNSS infrastructure for tsunami warning, and then I'll look at what Australia is doing in terms of providing infrastructure for this purpose. So what we've done to upgrade the GNSS network and developing software that will enable us to produce products which can be used for tsunami warning. And then finally, I want to present some results of a case study where we were actually looking at GNSS observations from LEO satellites for ionosphere mapping that might be useful for augmenting ground-based ionosphere results. So this map shows sources of tsunamis over the last 400 years. They're color-coded by the number of deaths each tsunami have caused. As you can see, most of the more deadly earthquakes are around the Pacific Rim of Fire, as people have talked about, and in the Indian Ocean to a large extent. Over these 400 years, these tsunami events have resulted in approximately 500,000 deaths. So this is obviously a significant problem which needs to be addressed so that we can provide warnings so this doesn't continue into the future. Just by way of some statistics, on the left-hand side, you're looking at a pie graph which shows you the sources of tsunamis. What you can see from this is that earthquakes are indeed the leading cause of tsunamis, although there is a fairly large fraction of them that are generated from non-earthquake related sources like landslides and volcanoes. On the right-hand side, you can see the breakdown of tsunami sources by ocean basin, and you can see again that the Pacific Ocean basin is by far the largest source of tsunamis and tsunami deaths at the moment. And from this, you can also see that since 1980, we've had about 250,000 deaths from tsunami, which is largely resulting from the Sumatra 2004 earthquake, but still that's a large number of people who have died as a result of tsunamis. And the other interesting statistic, which is important to keep in mind, is that a lot of deaths, 60,000 in this case, have actually resulted from tsunamis whose source was over 1,000 kilometres away from where those people died. So our global monitoring capability is certainly something we need to keep in mind. So what's the Australian government tsunami warning system look like at the moment? So as I've talked about, Australia has a fairly large exposure to tsunamis. We have 8,000 kilometres of coastline, which can be impacted within 2 to 4 hours. And we would like to have a requirement of being able to give people warning at least 90 minutes in advance of those areas being impacted by tsunamis. The main effort to develop a warning system began after the 2004 Sumatra earthquake and tsunami, where it became obvious that we needed a much better warning system. And the Australian government established both a National Earthquake Alert Centre which is operated by Geoscience Australia, and also the Joint Australian Tsunami Warning Centre, which is jointly operated by GA and the Bureau of Meteorology in Australia. And the mandate is basically to monitor, detect, verify earthquakes and provide warnings of tsunamis that might be impacting the Australian coastal regions and their offshore territories. So as I talked about earlier, the problem of tsunamis is global. There are some countries that have very sophisticated systems, as we've seen, for detecting and monitoring for tsunamis, but there are also large portions of the globe which have none or very minor tsunami warning capability. And this is something which needs to be addressed by the global community. And as I mentioned earlier, monitoring your local region for tsunamis is good, is useful, but also we need to be cognizant that earthquakes or tsunamis that are generated from earthquakes for very distant sources can also be devastating for a lot of regions. At the moment, tsunami warning systems are broken down into two types. There are tsunami service providers, TSPs, and there are National Tsunami Warning Centres, NTWCs. And these centres work together to provide 24/7 early warning down to local levels, basically providing coastal forecast zones. In Australia, we operate the Joint Tsunami Warning Centre, which operates both as a TSP and an NTWC. So the system as it operates currently in Australia is we have a network of around about 100 real-time seismic monitoring stations and 6 deep ocean buoys, and a network of coastal tide gauge stations. These provide fairly sparse point source data, which is used for data into the tsunami warning system. The system also relies on a real-time global network of shared seismic data and sea level data in order to detect the earthquakes which are producing these tsunamis. So the current capability is basically a 24/7 real-time earthquake detection system, which is capable of characterizing and defining earthquake sources, which are driving tsunamis. The system is capable of taking those sources and then producing tsunami models, which contain wave heights and arrival times at land masses, basically from forecast models. And these are then used to determine which coastal zones are under threat from particular tsunami events. And then from there, the warnings are issued through national chains through triggered events. So the current challenge is basically improving the accuracy of tsunami early warnings. The accuracy is largely dependent on the sources, which are derived from earthquakes, and these are inversions of data. And when we have good, well-observed sources, the models are fairly good, but these actually are only proxies for the actual phenomenon. So we're not actually observing directly the tsunami themselves, we're actually observing the earthquakes, which are then used to build the tsunami models. So if the models aren't good, then our forecasts of the tsunami impacts will also not be so good. We have some direct observations of the tsunamis that are generated through deep ocean buoys called dart buoys, but these are relatively sparse, and you basically have to wait once you've generated your model for your tsunami to pass through these dart gauges before you can actually know whether your new model was useful for detecting the tsunami or not. There are ways of densifying these monitoring systems through smart cables and things like that, but in some regions it's not really practical to run these systems, and they're quite expensive to deploy as well. So what does an ideal tsunami warning capability look like? What we'd like to have is a 4D observation system that allows us to look at the Earth's or the ocean surface in 24/7 in real time. And the question that we're putting out there is, are there existing satellite-based technologies that can provide this solution? And if they're not there yet, how close to getting these are we? And can they be operationalized into a system that can provide these warnings? So just a little bit on what's been done to date. So as a lot of the other speakers today have talked about, monitoring of the ionosphere, which is also a proxy for waves in the ocean, has been shown to be a possibility for over a decade now. So we have lots of examples of in the literature of how this might be done, how we might be able to use GNSS signals to actually observe tsunamis in the atmosphere. And there's even one system now, which we saw at the beginning of this workshop, of a system where it has actually been operationalized. So we can actually get operational GNSS observations of the ionosphere, which show how tsunamis are propagating in the ocean. So I just want to touch on now what Australia's been doing to improve its infrastructure for GNSS monitoring. This map shows you a picture of Australia's National Positioning Infrastructure Capability Network. This has been developed and augmented over the last 5 years to be pretty much in the state that you see on the left-hand map. It's a bit hard to see, but the pink dots are some of the stations that are still left to be installed, which will give us the final coverage of most of the Australian continent, with an average spacing of around 200 to 300 kilometres and much denser on the east coast and west coast, as you can see. So this is just a picture that shows you what the new modernised NPIC stations look like. These systems have dual GNSS receivers. They are running at 1 Hz sampling rate. They have real-time comms and quite an amount of redundant power in those boxes. At the moment, we've upgraded 130 of the reference stations in Australia, including installing 70 new stations to fill gaps in the network that existed prior to this project starting. And as Viliami pointed out, Australia also helps maintain a network of 13 real-time GNSS core stations in the Central and South Pacific, and those stations are also being upgraded to bring them to a similar standard to these stations in the Australian network. So Australia's NPIC network is operated through a control centre in Canberra here at Geoscience Australia. The map on the bottom left shows you a picture of all the core stations that are currently available in the database. The blue dots show the stations which are available in real time, so they have a real-time stream attached to them, which you can connect to through GA's Ntripcaster. And the Operations Centre also provides access to the metadata as well as the actual recorded RINEX data in the database as well. So all of that's available through the links that I've put up there in the top right. Another thing that Geoscience Australia has invested in recently is a project to provide some software infrastructure for actually analysing the GNSS data which we collect. This project is called Ginan, and the project is building a multi-GNSS undifferenced uncombined data analysis capability. The software is open source, and it is capable of delivering positioning services for both real-time and post-processed applications. And when completed, it should be able to deliver sub-decimeter level accuracy positioning anywhere in areas where you have IP or internet coverage to receive the corrections. And as I said, it's called Ginan, is the name we've given it. So how is Ginan related? So Ginan is a state-based representation, uses a state-based representation methodology. I'm showing you the observation equation here for GNSS observations. Essentially, what Ginan does is it parameterizes most of these terms in this observation equation, and it enables you to generate an estimate of those states. And one of those states, as is shown in the red box here, is the ionosphere, or the total electron content of the ionosphere between the station and the satellite. And Ginan is capable of generating these unbiased slant total electron content observations with every time step of the Kalman filter, which we've implemented. The main reason for building these, or for building the system, was originally to deliver corrections to enable PPP RTK positioning, but the ionosphere is also, as we've seen, a useful tool for doing observation of tsunamis in the ocean. I won't spend too much time on this slide because I don't want to take too long, but the idea is that GNSS observations enable us to basically measure what is happening in the ionosphere as waves propagate through them. This is enabled because the ionosphere is dispersive and different frequencies are delayed and refracted by different amounts by the ionosphere. So by observing on multiple frequencies or multiple GNSS frequencies, we have a way of then tracking what's happening in the ionosphere. And you'll hear people refer to these waves or these disturbances in the ionosphere as TIDs, or traveling ionospheric disturbances. And that's where the information on what the process is that's produced those ionospheric disturbances can be inverted to gain some insight into what's physically happened on the Earth. So a lot of people have talked about ground-based observations of the ionosphere. What I wanted to show you today is the start of a case study that we've been using Cubesats to look at the ionosphere from space, rather than just restricting ourselves to looking at the ionosphere from ground-based observations. So this was a little EOS opinion article that we published at the end of last year, showing some of the results I'm going to show you, and trying to build some momentum around potentially some approach to having a system on orbit that we might be able to use to augment the existing terrestrial GNSS observations. I think everybody's seen this video lots of times. This is the HTHH eruption on the 15th of January last year. And this was the source of a large amount of energy which propagated through the Earth's lower atmosphere and up into the ionosphere. And that is what I'm going to be talking about today, is what that looks like when you observe it from an orbiting platform rather than a terrestrial platform. So the data set that we've been using for this study is coming from the Spire global Cubesat constellation. These are very small satellites. They're 3U, so they're 10 centimetre by 10 centimetre by about 30 centimetres. They weigh about 6 kilograms each. They're orbiting at altitudes of 400 to 600 kilometres in sun-synchronous orbits. They have a lifespan of about 2 years. Currently, I think Spire Global has launched about 150 of them. And these satellites are carrying dual frequency GNSS receivers, and they have both a zenith-looking precise orbit termination GNSS antenna, as well as a sidewards-looking high-gain radial occultation antenna. They're doing occultations of the atmosphere. So what does this look like? On the left is a picture which shows you a LEO satellite which is orbiting the Earth at around 600 kilometres or so. What you can see from this is that the satellite is actually in the ionosphere. So what you have to remember when I show these results later is some of the results I'll show you are looking at the ionosphere from the zenith of the LEO satellite, that is the upwards looking antenna. So we're only observing the top of the ionosphere, not the bottom in these studies. And then the second set of observations I'll show you is when we've used the radio occultation antenna on these satellites to look sideways through the ionosphere, which gives us a view of both the top and the bottom of the ionosphere, or a profile through the ionosphere in that case. So this is a little bit busy, these slides, so I'll try and take a little bit of time to explain what you're looking at. So in the far left-hand column, what you're looking at are maps of the Earth, where the coloured arc going from blue to yellow is the path of the LEO satellite that we're have the GNSS receiver on, and the red arc is the path of the GNSS satellite over that same time. And that star with the blue dot in the middle of it is actually the HTHH volcano eruption. And then on the left-hand color bar, you're seeing the time that the satellite was visible to the GNSS satellite. So the LEO was visible to the GNSS satellite. So blue to yellow is the time in hours that that satellite was visible to the GNSS satellite. So in the middle set of plots, what you're looking at is the TECU, the ionosphere measurements, or the slant TEC values between the satellite and the LEO, the GNSS satellite and the LEO. And the first column is time on the x-axis, and the second column it's the same plot, but it's longitude on the x-axis. So basically what we're looking at is how the TECU is changing through time in these plots. So first column is right after the explosion. In this particular path, we don't see anything. You can see the TECU is very smooth, and there doesn't seem to be any traveling ionospheric disturbance in it. If we look sometime later, in the second row, you're looking at basically an hour and a half after the eruption. What you can see is that the blue circle is showing that the wave in the ionosphere that's been produced by the explosion has expanded, and you're starting to see this traveling ionospheric disturbance showing up in the TECU observations in that period from about 6.25 hours to 6.5 hours. And again, the two columns are showing you the time and longitude propagation of those waves. And so you can just, what the further rows are showing you are just different times and satellites view of the of this T-TEC wave that you see propagating. And contained within that waveform is not a single wave that's produced by the explosion. It's actually multiple waves. There's an acoustic wave, there's gravity waves, and then there are some enhanced harmonics of the tsunami in the waveform as well. And we haven't actually quite yet figured out how to invert this waveform, but that's part of the research team is actually looking at that now, is how we turn these waveforms in TEC into waves out in the ocean. So just to show you that this seems to actually work, this next plot shows you basically, sorry?
I'm sorry to interrupt. We're reaching the 20 minutes mark.
Okay, I'll just take one more minute if that's okay.
Thank you.
So the left-hand column shows you the day before, and the right-hand column shows you the day after. So it's quite clear that what we are observing in the ionosphere is associated with the explosion of this volcano in this case. I'll skip over this slide. It's basically a stacking of similar events showing the different peaks of the different waves in the ionosphere. What I wanted to show you was the results of the occultation measurements just quickly. So in the top row, you're looking at the day before the explosion of an occultation through the region where the wave will pass in the following day. You can see the model, the International Ionosphere model, matches very closely what the Cubesat is returning in terms of ionospheric profile of where what the density of the ionosphere is at particular altitudes. And the day of the earthquake, the interesting thing is that what we see is that the bottom of the ionosphere has been lifted up well above where the model would put the ionosphere. So essentially the ionosphere is being pushed up by the explosion, and we can't actually observe it anymore with the occultation. The ionosphere is actually flat. There is no ionosphere to observe. So it's all been pushed up quite a distance by the explosion of the volcano. And that's just another example of it. We see it in multiple places at multiple times. So that was something interesting that we didn't actually expect to find when we were looking at this data. And so that's the end. I'll leave you with this slide, which was the wish list of things for an early warning tsunami system that was put together by the community safety branch who operate the tsunami warning system. I'll just leave it on the screen. People can look at it in the recording if they're interested in the details of what might be ideal. Thanks.
Thank you very much, Simon. Presentation, especially the measurements of the topside ionosphere. I might have a few questions on that a bit later if we have time.
Sure.